So we want to go on and look for a solution of this differential equation. So this is a second order homogeneous and linear differential equation for the function ex of z. And if you want to solve them, then you should talk to a mathematician, and he will tell you try to use the exponential function. So we use as a trail function that we assume that we can say ex of z is somehow a constant, e naught I call, times the exponential function of minus j beta times z. So, and the nice thing of the exponential function is now its behavior if I consider the derivation with respect to z. So if I apply the derivation with respect to z to this function, then of course you see we must apply the derivation to the exponential function. And of course now the exponential function will reproduce itself, but we must multiply with this term, so we will get minus j beta times e naught exponential function of minus j beta times z. And of course you see that, that the derivation with respect to z goes over into a multiplication with minus j beta. So we can say this is minus j beta ex of z. And of course if we do a second derivation of this function with respect to z square, then this is the first derivation, and we will have then j beta derivation of the function again with respect to z, and we know this goes over into a multiplication with minus j beta, so we have here minus j beta times minus j beta times ex of z. So as a result we will get the second derivation of the function ex of z. So we have here minus times minus j plus minus beta square times ex of z. This results that we can substitute the derivation by this constant here, and of course we can include this into our differential equation. We will have to write then, instead of the derivation, we multiply with minus beta square times ex of z plus omega square mu naught epsilon ex of z is 0. So here we have two times the function, so we can say we have minus beta square plus omega square mu naught times epsilon times ex of z, it's 0. So since we have a homogeneous differential equation, always we will have the trivial solution that the function disappears, but if the function disappears there would be no electric field and it would be not interesting for us. So the non-trivial solution is given by the fact that this term must be 0, or we can say that beta square must be equal to omega mu naught epsilon, or beta must be chosen to be equal to omega the square root mu naught epsilon. But you see here, due to the point that the square root exists here, we will have in principle two possible solutions. We can once choose the positive sign and once the negative sign. This problem we will discuss later, though in the first step we will use the positive sign. And we know, for example, that the function h of z is given by minus 1 over j omega mu naught, derivation of the ex of z with respect to z. And we know that this must be replaced by beta, while we take the positive function and we find that h of z will be given by, so if we include here minus j, you see the j will disappear and we will have beta over omega mu naught times ex of z. So in principle we found now the solution. As long as we choose beta to be equal to this term, this function would be a solution. And also we found here the function for the magnetic field also. So up to now we found from a mathematical point of view the solution. So we found that the trail function would solve our differential equation. So the solution will be E naught. This is an arbitrary constant at the moment, times the exponential function minus j beta z. But we must choose beta to be equal to this term. And for the magnetic field, we found now that the magnetic field is proportional to the electric field, the magnetic field in the y direction proportional to the electric field in the x direction. And here we have a special term, so we will insert this term and we will see this is omega times the square root mu naught epsilon divided by omega mu naught times ex of z. And you see here this will cancel, and normally this is written like this. This can be rewritten by 1 over the square root of mu naught over epsilon times ex of z. And here we have a certain constant, and normally we will define this to be the so-called field impedance. This will be the square root mu naught over epsilon naught. It's called the field impedance. The field impedance, and normally one introduces here a further value. We can rewrite this equation like the field impedance. It will be the square root of mu naught divided by epsilon naught times the square root of 1 over epsilon r. And here we introduce a further constant. This is z naught. It will be mu naught over epsilon naught. And this is called the field impedance in free space. And since mu naught and epsilon naught are both constant, we can calculate the value, and it's 377 ohm. This would be the field impedance in free space. And as soon as you insert a dielectric, then you will have, this is z naught divided by the square root of epsilon r. This means in a dielectric the field impedance will show a reduced value, but in both cases we will have that it's a real value. So the field impedance is always real. From a mathematical point of view, this means the magnetic field H and the electric field X at a certain point Z in space are always in phase. So there will be no phase deviation between the magnetic field and the electric field in free space. And we will later on discuss what is the meaning of this expression for the time, space and time functions. So in the first step now I want to discuss this function on a mathematical base. We saw that this is the electric field in the x direction has a certain constant which we have to choose, and then we must multiply with the exponential function of minus j beta z. So this constant we have to choose on an arbitrary base, and what I sketched here is the EX plane. This means it's a complex plane of the electric field. We have here the real part of the electric field, here the imaginary part of the electric field. And for example, we can think of that this term, the E naught, points somehow in an arbitrary direction in this plane. So this will be our constant E naught in this plane. And what will now this function do? This function will change the phase. So it only changes the phase, but leaves the value, its absolute value, constant. This means we can use, in principle, a compass. And what this term will do now is it will change the phase in clockwise direction depending on the angle beta times z. The angle is defined by beta times z. But you see here, due to the negative sign, we will turn the value in clockwise direction. And so the resulting term will be then that will be Ex of z. And you see, the further we propagate in the z direction, we will turn always, it will be turned by the phase beta times z depending on, on the distance z. And this is why beta is called the phase propagation constant. And in the next step we will discuss what will be the influence on this term for the real space and time function. Now I want to discuss the physical significance of our function. This is the so-called phasor notation, and we know that with the help of the phasor notation we in principle describe a real space and time function. And to come back to the real space and time function, we must now use the equation that the real time and space function z omega t oh sorry, it's a real function here, we have to consider the imaginary part of the function ex of z, and we must multiply this function with the exponential function j omega t. And I can include now, here in this case I assume that E naught is a real quantity, and we can rewrite then this as the imaginary part of E naught times the exponential function of, now you see we have the two terms, they will add in principle, j omega t minus beta times z. So, and then this constant is assumed to be real. I can put this in front, and we will get that we have E naught times the imaginary part of the exponential function j omega t minus beta times z. So, and we know that this is identical to the sinus function, so we will have this is E naught times sinus omega t minus beta times z. So I want to have a look onto this function now. So I draw a coordinate system. In this direction I will sketch the z coordinate, and in this direction I will sketch our function. But you see this function is a function of space and time, so I will have a look onto this function at a certain time instant, for example on the time instant t equal to 0, and then we will have here, this is a minus E naught of beta time, oh sorry, it must be written here, sinus beta times z. You see here the constant, so here I will write this is E of z at the time instant t. This is real function, we have a certain amplitude, that means E naught will define the amplitude of the function. Of course it will be a periodic function. So at t equal to 0, and it will be sinusoidal. So if I draw this function, it looks almost like this. We will have a sinusoidal field distribution. Along the z-axis at the time instant t equal to 0. And normally you define now, if the starting point, if I start here and the function repeats at a certain point here, then this is called normally the wavelength. Lambda. And according to this equation we can see that the wavelength, or beta, times the wavelength must be equal to 2 pi, or we will get as a function, as a result for the wavelengths, we can conclude that the wavelengths will always be 2 pi over beta. This is the equation which will describe our so-called wavelength. So we will later on discuss this in more detail. What we found up to now was that if I switch to the real space and time function, our solution is described by this function. And what we did is we sketched this function for a certain time instant, t equal to 0, and then we found that along the z coordinate we have a sinusoidal field distribution. So what we can do here is we can, for example, introduce here the term total phase. This is the total phase of the sinus function, and of course if I define this total phase, we can say this is omega t minus beta times z. So instead of discussing all phase points, I will now have a look to a certain point. This point would have the total phase t equal to 0, and what we will do now, I want to discuss what will happen to this point if t and z can be changing, or t, so we will have 0 here must be equal to omega t minus beta times z. From this you see that we can say beta z is omega times t, or this point z of this red point of total phase 0 will change with omega divided by beta times t. And you see this point with the total phase 0 will move in the positive z direction, and this must be a velocity, and of course we can include here beta, it's omega over omega the square root of mu naught epsilon times t, and what we see here, the omega will cancel, and we will see that we can say the phase velocity, it will be 1 over the square root mu naught epsilon. This will be the phase velocity of a plane wave, and we see here that this phase velocity will be equal, to 1 over the square root mu naught epsilon naught times 1 over the square root of epsilon r, and this is normally called z naught, and z naught is called the speed of light. In free space. This means the phase of our plane wave will propagate roundabout with the speed of light, but you see here it's c naught divided by epsilon r. So normally we will define c to be the speed of light in a dielectric. And you see that the speed of light in the dielectric will change. So if I have a look to this point here of a certain at a certain time instant. Perhaps I look here, Ex of z at a certain time t, then this point will move into the z direction, and not only this point but all points will move into the z direction. So you see that this sinusoidal field distribution will move with the speed of light in the z direction, and this distance is just the phase velocity times t. We can conclude from this, if I have a function sinus omega t minus beta z, that this describes a wave traveling in the positive z direction with essentially the speed of light. If we have a dielectric, the speed of light is slightly reduced compared to the speed of light in free space. On the other hand, we could say if I have here a positive sign, then you see we would have here a positive sign and here a negative sign. This results in the fact that the function with the positive sign here, it means beta has to be chosen negative, then this describes a wave traveling in the negative z direction. This we will summarize also in the next step. So I want to summarize now our knowledge about a plane wave. Up to now, we found as a solution for the wave equation that we have if I assume an electric field in the x direction, and this term will describe the propagation in the positive z direction, and we saw that this function will solve the wave equation, and to this electric field, which is directed in the x direction, we will have a magnetic field which is directed in the y direction. So the electric field will be perpendicular to the magnetic field, and of course it will be perpendicular to the direction of propagation. In our case it will be the z direction. And the propagation is described by the phase velocity in z direction, and we found that this phase velocity in the z direction depends on two equations. Though this term is identical to the speed of light in free space, we have 3 × 10⁸ meter per second. And if the plane wave is traveling in a dielectric, the speed of light will be reduced to a lower amount due to the relative permittivity. Associated with this wave is also the so-called wavelengths. We call this the wavelengths in free space. So in free space we have this is C naught divided by the frequency. This again means as soon as the frequency increases, the wavelength decreases. And if I have a wave in a dielectric, then again the wavelengths will be decreased by a certain factor, 1 over the square root of epsilon r, and again epsilon r will be the relative permittivity of the dielectric media. On the other hand, we will have here the so-called field impedance, and also the field impedance can be described by two terms. First, we defined this Z naught, it's equal to 377 ohm, which is the so-called field impedance in free space. And on the other hand, we have again the field impedance in a dielectric. It will be reduced by again 1 over the square root of epsilon r. This is then the field impedance in our dielectric. And here you see the phase propagation constant, and the phase propagation constant is related by this equation to the wavelengths. So we can distinguish between the phase propagation in a free space, then we have to substitute here lambda naught. If we are in a dielectric, then we have to substitute beta here, lambda here, sorry. So this summarizes up to now our knowledge about a plane wave.